Mhm. Okay. So yesterday we actually saw two important topics. One of them was related to what we call critical Mach number, and the other was related to drag divergence Mach number, and some physical concepts related to that. And basically, we have also covered some engineering solutions to related to transonic flight and basically transitioning into supersonic flight. As I told you, it was not very easy, and even sometime before World War II, people very strongly believed that it was not possible. But due to the basic physical better understanding of the physics of transonic flow and supersonic flow, some engineering modifications were made. We talked about two of them yesterday, actually three of them. One of them was using thin airfoils, basically. The second one is the area rule. We talked about area rule yesterday. And the third one is supercritical airfoils, which do have reasonably flat surface upper side or suction side, so which kind of pushes the strong shock wave towards back of the airfoil, and that generates a relatively weak normal shock wave. So the wave drag, what we call the wave drag, gets reduced. Another solution that enabled us to fly at transonic speeds and transition into supersonic speeds is the wing sweep. So what we're going to do is right now, we talked about area rule, and we will talk about wing sweep a little bit today. But before that, I would like to show you two short videos on that. Yesterday, I told you that regarding applications of this area rule and wing sweep. Two short videos, each one of them is about 3 minutes. So let's watch them, and in the meantime, we can discuss. First one is about area rule. So let me share my screen. Just a second. Sorry, I need to share also the sound. Okay, yeah, this should work. So let's watch this for first, then we can, if you have any questions, we can discuss.
There is a really simple rule that influences the design of every jet plane you've ever flown on in profound ways, and once you know about it, you'll start seeing its effect everywhere. It tells us why engines are placed slightly in front of wings, and why the fuselage of supersonic planes narrows along the wings, and why redesigning the hump of the 747 to be longer not only allowed it to carry more passengers, but also increased its cruise speed and decreased drag. This simple rule is called the area rule, and it tells us the ideal distribution of cross-sectional area along the length of a transonic or supersonic plane will look something like this. That includes the wings, engines, everything. Because a gradual change in cross-section results in a reduction in wave drag, which is the drag that arises from shock waves forming over the plane as it approaches the speed of sound. In reality, planes never achieve this ideal distribution. The Concorde's distribution looks similar to this, and could have been closer to the ideal had they tapered the fuselage over the wing, but more on that later. The rule was discovered as planes started to edge ever closer to the speed of sound, and designers started to notice that adjusting the position and shape of features on the plane had significant effects on performance. Take this patent from the Juncker company in 1944, showing obvious attempts to experiment with the distribution of cross-sectional area along the length of the plane, with the cross-sectional areas highlighted here. This ultimately led to the bizarre-looking Ju-287. The effect was discovered again by Richard Whitcomb when testing models in a wind tunnel in the 1950s. His discovery was used to redesign the F102 Delta Dagger, which was originally designed with a straight fuselage. The redesign tapered the fuselage over the wings and allowed the distribution of cross-sectional area to more closely resemble the ideal. This small change, along with slightly more powerful engines, brought its max speed from 0.98 Mach to 1.22. Sometimes it's not possible or does not make economic sense, as was the case for the Concorde, to narrow the fuselage over the wing. Instead, it makes more sense to make the fuselage before the wing larger, to make the change in cross-section less dramatic. The 747-800 featured a longer hump for exactly this reason, which allowed its cruise speed, passenger capacity, and fuel economy to rise. This rule even affects the placement of engines. Most large planes mount the engine slightly forward of the wing and not directly under, as that would compound the wing's addition to the cross-sectional area. And in narrow-body planes, the engines are often mounted above and behind the wing for the same reason. There are countless other examples of this rule that you can find in the real world, and I challenge you to name some of them in the comment section below. I'll pick out my favourite one and send you a free Real Engineering t-shirt.
Yeah, so yesterday I think I told you about this F-102 aircraft, the Delta Dagger, which was originally designed to fly supersonic with a delta wing, but it was not able to fly supersonic due to high wave drag because of the basically no area rule application. And after it was redesigned, as it said in the video, yes, then it went above supersonic. It was possible to fly supersonic. This, if you don't have any questions, we will watch the second video now, which is related to the fourth type of engineering solution, which is sweeping the wings towards backwards, I can say. So let's first watch this, and I will tell a few more words about this also.
Why are plane wings angled backwards? Today most planes have a swept wing design, and this helps the plane fly faster, but it wasn't always this way. Let's look back in time and learn how this technology was developed and what we learned in the process. Back in 1941, most planes were designed with a straight wing, and the Lockheed P-38 Lightning was no different. The straight wing design works well at lower speeds, but the P-38 was not a slow plane, and its engineers quickly discovered that the plane had major control issues in high-speed dives. On November 5, 1941, a Lockheed test pilot by the name of Ralph Verdon died when he lost control of his aircraft. This spurred a major investigation headed by an engineer called John Stack. He employed a special type of photography called Schlerin photography to observe the airflow in a high-speed wind tunnel, and this is what he saw. As air passes over the wing, the air over the top of the airfoil accelerates. This is how the wing generates lift. This means that a wing travelling at less than the speed of sound can actually develop areas of localized flow travelling faster than the speed of sound, and shockwaves form at these locations. These shockwaves will reduce the lift and increase the drag on the wing. The speed at which shockwaves begin to appear is called the critical Mach number, and Ralph Verdon reached this speed during his high-speed test dive. So why did this cause a crash? As the speed of his plane increased even further, the airflow from the surface of the wing separated due to the shockwave formation. This separated flow actually increased the lift on the tail wing, and this combined with the reduced lift on the wing caused the P-38 to enter an even deeper dive, one that was very difficult to escape from. John Stack solved this problem in 1943 by placing a special flap under the wing, where the flow was not being affected by the shockwaves. This flap could be deployed during dives and would increase the lift on the wing to maintain proper pitch control. Over the next decade, John continued his work in the development of supersonic flight, and was a major driving force for the development of the Bell X-1, which was the first manned vehicle to break through the sound barrier in 1947. The Bell X-1 was a rocket-powered plane, and its fuselage was modelled after a .50 caliber round, which was known to be stable in supersonic flight. Its engineers increased the critical Mach number of the plane by using a very thin wing, and avoided the pitch control issues of the P-38 by raising the tail wing up and out of the downstream airflow of the wing, but this plane still had a straight wing. The realization that the swept wing may hold the key for high-speed flight came at the end of World War II. In 1951, the Bell X-5 was released, and its design was mostly based on a captured German prototype. The Bell X-5 had the special ability to change its sweep angle during flight, making it the perfect test subject to investigate the aerodynamic advantages of the swept wing. Let's compare the aerodynamics of the straight-wing Bell X-1 and the Bell X-5 as it increases its sweep angle. Air over a straight wing will flow parallel to the chord only. This is called the chordwise flow, the air that accelerates and creates lift. As explained earlier, it is this acceleration that reduces the critical Mach number of the plane. Now let's look at the flow over the Bell X-5 as it increases its sweep angle. A swept wing introduces a new component of flow, the spanwise flow. This flow runs along the length of the wing and does not accelerate, and thus does not affect the critical Mach number. By converting some of the airflow into spanwise flow, the acceleration of air over the chord is reduced. This means the plane can fly faster before shockwaves begin to form over the wing. As the plane increased in speed, the pilot could increase the sweep angle. Doing this converted a larger volume of air into spanwise flow, and thus increased the critical Mach number even more. This test proved that the swept wing design could delay the formation of shockwaves and thus allow planes to fly faster. So next time you're flying, take a look out the window and admire the engineers of the early 20th century. Their designs have allowed us to travel across the globe at transonic speeds, and hopefully soon regular citizens may break through the sound barrier once again. Thanks for watching. If you want to learn more about the mechanics of the swept wing, click on my website here. For my next video, I'll be
Yeah, okay. I would like to say a few words. Maybe with using the whiteboard regarding the wing sweep. Do you have any questions about these, first of all?
Göremiyoruz hocam, şu an ekranınız yok.
No, I mean, do you have any questions about the
Sorry,
videos?
pardon.
I will share my screen in a second. Regarding wing sweep, actually, it has also quite interesting history. Of course, wing sweep is needed for transonic flight and for supersonic flight, which basically started to happen or started being applied after World War II in late 1940s and 1950s. But this idea was proposed by a German engineer, Adolf Büsemann, in 1935 at a conference, at an aerospace conference. And he actually proposed the fact that the aerodynamics of the wing is actually dominated, and the lift generation and CP distributions are basically dominated by the vertical component of the velocity, that is the component of the velocity that is vertical perpendicular to the leading edge. Okay, so therefore by sweeping, so the thing is, when you start to fly, let's say your M infinity, this has a certain airfoil section, and you have some infinity approaching, and basically what happens is, if it's not swept under normal conditions with zero sweep, as it was said in the video and as we discussed yesterday, we start to see supersonic regions, and as the M infinity increases, these supersonic regions becomes more and more bigger and bigger. Now, and then we reach a certain drag divergence Mach number, the drag suddenly increases a lot, and that sudden increase in drag is basically due to two reasons. One reason is due to a strong shock wave at the end of the supersonic region, close to a normal shock wave that creates a big, what we call wave drag. And if you zoom in this region, let's say this is top of the airfoil, this is the airfoil, and we have a shock wave somewhere in between. And what happens is, you have this flow coming in, and in reality, we will see that in a few weeks, but and we have been doing our compressible flow analysis based on inviscid flow assumption, but of course, in reality, flow is not inviscid. Flow is viscous, and that generates what we call a boundary layer on top of the airfoil. We will see those in detail in coming weeks. But what happens is, because of the shock wave, there is a sudden big static pressure increase, as we have seen so far. This static pressure sudden increase basically causes this boundary layer to separate. So this generates a flow separation at the back. And if you zoom in here to this region, let's say this is the top, what happens is the normal shock wave comes here, and because of the flow is separating somewhere here, actually just near the normal shock wave, um, when the supersonic flow sees this separation line, it generates a small oblique shock wave. It's like basically acting like a ramp. And then it gets combined with this and then actually generates another oblique shock wave at the back. Now, this is called a lambda shock pattern. Lambda, it's called a lambda shock, very close to the body surface. This lambda shock wave pattern is a standard footprint of shock wave boundary layer interaction. It causes the flows to separate after the shock wave. So in addition to having the static pressure increase, which contributes to the wave drag, we have basically separated flow after this. And if your control surfaces are within the separated flow, they are ineffective. That's why the crash, that's why it happened, the crash that the guy was talking about in the video for P-38 during dive. Because of this, it had a straight wing. They did not know about this, of course, and the flow and they knew about this later after many wind tunnel experiments. And then because of the flow separation, the control surface became ineffective. Pilot couldn't, recover the aircraft, and it crashed. The pilot died, unfortunately. So but what Adolf Busemann proposed was the effective Mach number or velocity component that is responsible for generating this lift, and that is responsible because that's responsible for this wave drag and shock wave structure generation is the normal component or the perpendicular component of velocity to the leading edge. So if there's a possibility to sweep this back, basically what we are doing is we are changing the normal component of the velocity with respect to the leading edge. So if we have the same free stream Mach number, the normal component now will be tilted by a amount of sweep angle. So if the sweep angle is capital lambda, generally we use that Greek letter for that. So m infinity times cosine of capital lambda will be the perpendicular component to the leading edge. I mean, it could even be subsonic if the sweep angle is high enough. Even if this, which means that, first of all, even if this perpendicular component is supersonic, it will be less than your actual flight Mach number. So your drag critical Mach number and drag divergence Mach number will be pushed to higher levels, first of all. And if the sweep is even so high that the M infinity here, even if it's high, very high, close to supersonic, let's say, high transonic, your aircraft, the wing, the flow over your wing with a properly swept wing could still be like subsonic flight. So this was first proposed by Adolf Busemann, and actually nobody cared about this in this conference when he first proposed this. It's quite interesting. Everybody was attending this conference, von Karman and Dryden, all these hotshot guys of aerodynamics, they were attending this conference. They really did not care. They went back to the United States, and after the conference, they did not tell anybody about this. But when Busemann went back to Germany, Germans actually understood the value of this. And then in 1936, they classified this information. So decided to not to tell this to anyone because they wanted to build high-speed aircraft themselves. And then in Germany, Busemann later joined Prandtl's group at DLR, but DLR has a different name back then, AVA. And then what happened is they did lots and lots of wind tunnel tests, developed lots of theory, and actually developed high-speed, lots of swept wing aircraft. And when Germany lost the war, and Theodor von Karman was basically, he headed a group of engineers and scientists when United States occupied Germany. Von Karman came back to Europe from United States, and he led a group of scientists, and they went to these wind tunnels, and they actually captured all technical documents and transferred Buseman. They held Buseman captive and transferred him to the United States. And he started working at universities in the United States and at NASA and all that after that. But so they captured everything that is related to that Germans, all the information Germans produced regarding swept wing aerodynamics. But that happened in 1947, so I am just giving you a little historical information. That happened in 1947. But interestingly, totally unaware of Adolf Busemann's proposal and totally unaware of his work in the United States, another scientist, Robert Jones, I think his name. I think he was not even a college graduate, but he did learn aeronautics. He did take classes, and he was so talented that NASA hired him with doing lots of magic tricks to hire a person without university degree. They hired him to NASA, and he actually said he wrote a report about this swept wing concept, sent it to wanted to publish it as a NASA report, and talked about the swept wing concept in terms of transonic aerodynamics and how it can be implemented to fly faster. But it was he was very much rejected by, I don't know if you're familiar with this guy, Theodor Theodarsen. This guy is also a famous aerodynamicist, especially in aeroelasticity. You may hear his name a lot, but he rejected his report, and he said this is just observations not supported by mathematics. So he prevented the publication of this report for a long time. But after they captured German studies in 1947, they realized that Robert Jones was also working on the same thing. And then, of course, everybody started to apply also in the United States. Lots and lots of swept wing concepts. It's interesting history. But this effective velocity and in turn the CP distribution, pressure coefficient distribution, that is calculated using this effective velocity is very much, I think, very well explained in a relatively recent book chapter. I will quickly show that to you. And then I will actually, I think we will post it to Otto class. You can download it. Let me share this with you. First of all, where is it? Okay. So this chapter written in 2015, aerodynamics of swept wings, and this has much more information about the theory, especially if you read the first few chapters like 8.2.1, theory of wing sweep. They talk about what I was describing as the there was a figure about this. Let me find it. Yeah, like if you had a straight wing compared to it says oblique wing, but it's swept. By the way, sweep can happen backward and forward. It doesn't matter, okay? Backward or forward. Both aerodynamically, they are the same thing. However, and if you, I don't know if you're familiar, but there are indeed forward swept wing aircraft built by Russia and also built by United States. So, but they were all test experimental aircraft. The problem of forward swept wings was not aerodynamic, it was more aeroelastic problems those days, but their maneuverability was much higher. Anyway, so using the angle definitions and velocity vector definitions here, as you can see, the vertical component gets reduced and the tangential component gets generated. That's what the guy in the video was saying, the span-wise velocity was generated. So there are also relevant equations, simple equations that relate, for example, CP of an unswept wing, this in this equation 8.6 here, CP pressure coefficient of an unswept wing when lambda is equal to 0 to the CP of a swept wing through the sweep angle lambda. There are other details if you're interested. We will put this in Otto class. You can read more about this. Okay, and effects on drag divergence Mach number, as I just tried to describe conceptually, and effects on wave drag coefficients due to shock waves and everything. So all the details are here. Okay, any questions up to this point? So just to summarize, we have seen basically 4 engineering solutions that allowed transonic and supersonic flight: thin airfoils, area ruling, supercritical airfoils, and wing sweep. Okay, any questions so far? Okay, so then we will continue with our next subject. The next subject is again under, I think it is the last subject regarding compressible flows. Let me check quickly. Yes, this is the last subject regarding compressible flows. And we will watch this video together, and I will make comments. But just to explain you what we're going to talk about, let me first share this. Hold on a second. Yeah, okay, let's share this one. I hope I share the sound as well.
Hello everyone, this is
Can you hear the sound?
Evet hocam.
Evet hocam.
So let me quickly explain this. In the video, it will be explained more. But the thing is, what we covered so far is we obtained, for example, a nonlinear potential flow equation for subsonic flow, subsonic compressible flow, and we linearized it, and we, talked a lot about these subjects. And we talked about transonic flow related issues in terms of both theory and in terms of engineering solutions. But when we start flying supersonically, of course, when Mach number is greater than 1, we also need a proper theory to apply and to apply for force calculations that are generated on wings, lift and drag, and also pressure coefficient variations on wings. So this last part of compressible flow, after this we will start viscous flow subject, which is going to be quite different, and is the topic of linearized supersonic flow. So let's watch this together.
Dr. Mustafa Perçin. I am with you with probably the last asynchronous online lecture of aerodynamics 2. Probably from next week on we will have online synchronous lectures through OptiClass. Please follow the announcements regarding this change. Okay, so today's topic is linearized supersonic flow, and we will start with our linearized potential equation we derived in the chapter of subsonic compressible flow over airfoils, and the equation is written again here. As you can see, we have this 1 minus Mach infinity square term in front of the first in front of this first term in the equation. This term in brackets actually becomes is actually positive when you are in subsonic flow, because Mach infinity squared and is smaller than 1. But in the case of supersonic flow, as Mach infinity is greater than 1, then this term becomes actually negative. Well, it may actually seem an innocent sign change at the first glance, but it actually changes the physics of the problem completely. Well, you can actually infer this from the type of differential equations, partial differential equations. When you have depending on whether you have this being positive or negative. For instance, when it's actually positive, which means that you mean in subsonic flow, then you have an elliptic partial differential equation. But when you move to supersonic flow regime, in which case this becomes actually negative, then it means that you have a hyperbolic partial differential equation. Well, although it's not in the scope of this discussion of this lecture, but let me give you some information about this elliptic and the hyperbolic partial differential equations. In elliptic partial differential equations, there are no real characteristics, and any information propagates in every direction, or any perturbation propagates in every direction without any preference in direction at a finite speed. But in hyperbolic partial differential equations, there are characteristic lines, and then an information propagates along these characteristic lines. This is the main difference between these two types of partial differential equations, and you will actually see how it's related to the case that the case of subsonic and supersonic flows in the coming slides. Okay, let's look at our partial differential equation again, and let's reorganize it such that we have this lambda square being square root of -∞ square minus 1, and then let's assume that a function of x minus lambda y is a solution to the equation. Well, you can actually verify this by just calculating the second partial derivatives of phi hat with respect to x and with respect to y using this function, and then putting it back into this equation. And if it's satisfied, then it means that our suggested solution is really the solution for this partial differential equation. Okay, you can do these calculations by using the chain rule quite easily. Here phi hat is the derivative of this f function with respect to its argument, and phi f prime is, and f double prime is the derivative of this function with respect to second derivative of this function with respect to its arguments. Okay, and it's actually it can be calculated also the same way for the first and second derivative with respect to y here, and then as you can see, second derivative of phi hat with respect to x is f double prime, and second derivative of phi hat with respect to y is lambda squared times f double prime. And if you put these equations back into this above equation, partial differential equation, you see that this equation is satisfied. So which means that this partial differential equation is satisfied for any function of x minus lambda y. Okay, well, it may actually seems a bit disappointing again, because this f can be any function of x minus lambda y. We don't know which relation or which function it is, but then we know now that its argument is x minus lambda y, and then along x minus lambda y constant lines, our phi hat is also constant, and phi hat is of course is the perturbation velocity potential, you may remember. So you may want to actually calculate the slope of these lines, x minus lambda y equals to constant lines, and then if you calculate their slope, it turns out to be 1 over lambda, and that's actually equal to 1 over square root of -∞ square 1. And from the chapter 9, you may remember that this is equal to tangent mu, and mu is the angle of is the Mach angle actually. And this result actually tells us now that the lines along which this phi hat is constant are actually the Mach lines that we actually first saw in chapter 9 of your textbook. You may, if you don't remember, please go back and check what they mean. So let's look at an example here where we have a supersonic flow over a wall with a hump here, and as you can see, we have these phi constant lines plotted as well here. So first of all, you should realize that this phi hat constant lines are have a slope in the direction downstream over the wall, because their slope is defined as 1 over square root of minus infinity square 1, and if you have a supersonic flow here, then they become positive, and as a result they are actually sloped downstream over the wall, which means that any perturbation that's generated on the wall or due to hump will not be able to, as you can see, will not be able to propagate upstream. They will propagate downstream along these Mach lines. So this actually now is in accordance with the type of partial differential equation, because this is a hyperbolic partial differential equation, and in hyperbolic partial differential equations information propagates along characteristic lines. So there is actually a preferred direction for the propagation of the information, and as we can see here in the physics of supersonic flow as well, we were always telling you that if you have a supersonic flow, then your information or any perturbation you generate in the flow will not be able to propagate upstream. They will all propagate downstream, and this is actually the case as you can see here. So however, in the subsonic flow case, any disturbance, any perturbation you generate in the flow can actually propagate upstream. Look at this problem again. So we see that any disturbance at the wall, any disturbance at the wall will only propagate downstream, and its effect will be limited in the region of the flow downstream of the Mach wave that's emanating from the point of disturbance, right? So the effect of this disturbance you generate here will only be felt downstream of this Mach wave actually. So of course, well, this is a linear theory, and then I need to tell you that this only valid. This solution is only valid if the hump is small, which means that your flow deviation angle theta is small. But it's actually, well, it's not that much different. If the hump is not small, in that case you would have actually you don't have a linear solution, of course, but then you will have a shock wave and expansion wave on the front and on the back sides of this hump on the wall. So well, I should actually say that at the end this linearized theory is an approximation, and as a result of this approximation, this waves of finite strength like the shock wave and expansion waves are not actually admitted here in this linearized supersonic theory. Okay, let's look at the pressure coefficient now. So in order to get the pressure coefficient in terms of the flow deviation angle, let's start looking at this u perturbation velocities u hat and v hat, and let's try to represent them in terms of this function f. And then u hat is of course f prime, because it's d phi hat over dx, and then v hat is likewise d phi hat over dy. It's lambda times f prime as well. Then if you use these two expressions, it turns out that your u hat is minus v hat over lambda. And then you may recall the flow tangency boundary condition from the previous chapter, that along the wall you need to have v hat being equal to v infinity times tangent theta. Theta is of course flow deviation angle. Then instead of v hat here, you can actually insert u minus u hat times lambda, and then if you do that, and then assuming that your theta is small, then you end up with a relation between u hat and theta as shown here. So let's look at the linearized pressure coefficient. Then it's minus 2 u hat over v infinity, and instead of u hat you can actually insert this relation here. Then you end up with 2 theta over lambda, and as lambda is this is defined with this expression. Then your Cp is 2 theta, where theta is the flow deviation angle, divided by square root of minus infinity square minus 1. Okay, let's look at this case. This theta definition is positive when it's actually for actually left running waves, when it's actually above the horizontal, then it's defined positive. When it's actually below the horizontal, it's negative, which means that in front of the hump here, of course, your flow deviation is positive, and below on the rearward part of the hump, then it's negative, which means that if theta is positive, you have positive CP here. For the rearward part, you have negative CP, and as a result, you end up with some finite drag on the hump, and this is known as the wave drag. And even though there is no shock wave in the linearized theory, you again end up with the wave drag also in this case. Okay, well, I told you that this theta definition is only valid for left running waves, but then for the right running waves, it's just the opposite here. When you are looking to right running waves, then theta is defined positive below the horizontal, and then it's defined negative above the horizontal. Or you can actually use another strategy. When the flow is deviated towards itself, then theta is positive, like here and here. It's actually deviated or turned into itself, and if it's turned away from itself, then theta is being negative, like the rearward part of this shape. Okay, let's consider a supersonic flow over a flat plate at small angle of attack, and in this case, of course, the flow deviation angle on the lower surface of this flat plate is positive because it's turned into itself. Then you have positive alpha here. Then you have then your CP lower is defined, is represented with this relation, and on the upper surface, because your deviation is kind of away from itself, away from the flow itself, then it's actually negative here. Then as a result, you have -2 alpha here, and which is also expected, because you expect to have high pressure on this side than the lower pressure on the upper surface. And then if you just use the integral from 0 to chord length, Cp lower minus Cp upper, in order to calculate the normal force, you end up with the normal force represented by this term. And axial force, on the other hand, is 0, because flat plate has 0 thickness or infinitely small thickness. Then using the CL and CD relations with Cn normal force and the axial force, and assuming that the angle of attack is small, being sine alpha approximately is alpha, cosine alpha 1, then you can actually get the CL and CD terms as shown here.
Okay, I think I will have to go over this video again, because there are many things that I guess I need to explain. But before that, and I will partly do this in the remaining 5 to 6 minutes, but I will do this also next week. But first of all, questions. Do you have any questions here? Did you understand what Mustafa Hoca was talking about in the video?
Hocam, I think I missed something about that hump part in theta. I'm sorry, mu angles.
Okay.
I didn't understand that part actually. Even if there is no shock wave, we have something a wave drag, I think.
Yes, that's good. That's good. It's important to know what you did not understand, and it's important to be able to state what you did not understand. Some people does not understand what they don't understand, so that's a problem. But I guess you have a point. It makes sense. I will explain it. Any other questions? First of all, I just want to explain, let me see if I can rewind this video to show you this sketch here. So first of all, guys, We are talking about linearized supersonic flow, and we are talking about, yes, we are talking about a supersonic flow, but there are no shock waves. Okay, there are no shock waves. There are no shock waves, there are no expansion waves, nothing. So we just have this solid surface, right, in the bottom, and we have supersonic flow over it. Even if you forget about the hump, yes, let's say it's perfectly flat surface. And we have this M infinity coming from left, which is supersonic. In a supersonic flow, first of all, we have these what we call characteristic lines. Okay, these characteristic lines are these lines that you're seeing here, and they correspond mathematically to these phi. I guess that needs to be phi hat equals to constant lines, as I guess discussed in the previous slide. Yeah. So what does that mean? I mean, there are no shock waves, nothing. These are what we call and what we defined previously as Mach waves. What does that mean? And this line is a Mach wave, and it is oriented at a certain angle mu, and it's this certain angle mu is equal to yes dy dx, and this is equal to 1 over square root of m infinity square minus 1. So it does have a positive slope. So it is in reality inclined back towards back like this. So they are indeed like that. But what do we mean by Mach waves? Which means this: let's say you have you don't have a hump. You have a wall at the bottom, no hump at all, perfectly straight wall. And let's think about a hypothetical case. Hypothetical means which does not exist in real life, right? A hypothetical case in which the surface is 100% smooth, okay? It is so smooth that when the flow is, it does not, on any point on this surface, it does not create absolutely no disturbance to the flow, okay? No disturbance. Of course, that's not realistic, right? We cannot, I mean, no one can manufacture such a surface in the world. So our surfaces are always have some kind of roughness. Maybe they are very little rough, very low roughness values, but they always have some kind of roughness, which means that our surfaces will always generate little disturbances to the flow. Well, if that's the case, and I'm still talking about a surface without a hump. So in this case, let's say we have a flat surface with some kind of roughness on it. And if there is some kind of supersonic flow passing over it, any disturbance created by any minute, very little, minimal roughness element will propagate along this Mach line. That information, that little disturbance created by this little roughness element on this surface will follow the Mach line wherever it is generated first and propagate along this Mach line. It will not, for example, propagate upstream because the Mach line is tilted backwards, not tilted forwards. So that information will never reach upstream. That is the main characteristic of supersonic flow. And in reality, it is different in subsonic flow. In subsonic flow, if there is a tiny, minute disturbance on the surface, that information gets propagated in every direction. Okay? So fluid particles all around know that there's a disturbance. That does not happen like that in supersonic flow. Any minute disturbance gets propagated along these lines, which are aligned, which are basically Mach lines and aligned at a certain angle, and that angle is perfectly determined by your Mach number. Okay, so first of all, let's make this point clear. Okay, make this point clear, and then and we are trying to solve this problem. No shock waves, nothing. We have these Mach waves. Any disturbance that are created will propagate along the Mach waves, and this flow field is governed by this previous equation that we saw in the video, the linearized version of of the potential flow equation. But since we are in the supersonic regime, this 1 minus m infinity square becomes a negative number in that differential equation. When it becomes a negative number, mathematically, it becomes what we categorize in mathematics as a hyperbolic partial differential equation, okay? And in reality, mathematical hyperbolic partial differential equations, they have they represent, I can say it like that, I guess, physically they represent exactly this kind of characteristic. Information always propagating towards downstream, no information absolutely gets propagated upstream. This kind of behavior mathematically is represented by hyperbolic partial differential equations, okay? So therefore what we observe in nature is consistent what we get from theory, such that the linear supersonic flow equation is a hyperbolic partial differential equation. Okay, I would like to say a few more words, then we will stop and I will continue on our next class. So this is that. Is this point clear, first of all?
I think yes, hocam.
Yes, okay. Now I'm slowly coming to your question, okay? So then we introduce a hump. So the thing that, I mean, in addition to, I don't know, some roughness, for example, could be introducing some disturbance. But let's say we have a little hump, and this hump, when I say little, I mean little. I mean, this is not like a full ramp like we have seen previously. It's a small hump, and the presence of this hump also creates certain Mach waves, and this disturbance is basically propagated. And then if it was not a small hump, then what happens is what happens would be what we have already seen before. There probably at the front of the hump there would be some oblique shock waves, not Mach waves, oblique shock waves, and at the back of the hump probably there would be some expansion waves. The flow would not be linear. The linearized supersonic flow equations would not be valid. Okay, so we are basically talking about a small disturbance that is happening, that is created by this hump here. So let me fast forward somewhat more.
Theory is an
okay. Yeah, actually the rest is that if this hump is creating some perturbation velocities like U hat and V hat, like we did before for the subsonic compressible flow case, and by the way, since we have a hyperbolic partial differential equation that governs the linearized supersonic flow, now we developed a specific solution, right? We said, okay, this is, I mean, we applied the solution procedure for a hyperbolic partial differential equation. We said, okay, this is solution will be of the form x minus lambda y, for example. Whatever that function is, a function of x minus lambda y, whatever that function is, we are assuming that it's a solution, and we started from there, and we obtain these change of variables, and then we related to, in this slide, we related them to U hat, V hat, and all that differentiation. At the end, we got an expression now for the CP, pressure coefficient, for this supersonic flow over this supersonic flow over this plate, but with a little hump on it. So this theta is that little disturbance created by the hump. So was your question related to this?
Yes, hocam. I think I understand now.
Mm-hmm. Okay, so anyway, it's already 2:35. I'm stopping here, but I will revise this. We will go over this video and revise this linear supersonic flow again. One final thing, I think it was not explained in the video, is if I go back here, is this. Mustafa was talking about, for example, left running and right running at some point, yeah? which means I will explain this point later in the coming class, but normally, let's say these waves, for example, are okay. This is how we do things. Imagine yourself, you are in the supersonic flow, but you're not facing the Mach number. You turn your back against the incoming flow, so you're facing the downstream direction. When you face the downstream direction, for example, the disturbance created by the presence of your body will propagate along two Mach lines. When you face downstream, one will be towards your left arm, one will be towards your right arm. Okay, so when you face downstream and look at downstream, and your flow will be hitting from your back. Imagine you are doing this. So we call, therefore, for example, these kinds of lines left running characteristics, and the other, I mean, in the sketch you don't see it, but you see it in the very final one here. For example, we have left running characteristics and also right running characteristics as well. Okay, that's why Mustafa Hoca was saying left running characteristic lines when he was discussing this. Good. Let's stop here. I will again, as I told you, by the way, there are no classes next week, as you know. Spring break plus Bayram. So after the break, we will meet again on Wednesday, and I will revise these points and go over these points again.
Hocam çok hızlı bir soru sorabilir miyim?
Ha, tabii ki.
Bir önceki şekle gelir misiniz bu hump'ın olduğu kısma?
Hı hı.
Burada biz hump'ı çok küçük olarak tanımlıyoruz ama theta beta m relation'ın tablosunda çok küçük angle'lar için bile olsa bir şok dalgası için bir şok oblik beta elde edebiliyoruz. Herhangi bir o upstream mah için.
Hı hı.
Burada diyoruz ki çok küçük hump olduğu için şok oluşmayacak.
Hı hı.
Bunu neye göre, bu approximation mı kabul edilir mi, yoksa her zaman şöyle ben atıyorum bir kural var mı? Belirli bir şey için şok olur, belirli bir şey için şok olmaz tarzında.
Ya buradaki hump'ın çok küçük olduğunu düşünüyoruz. Yani daha önce hani linearize etmek için denklemleri, hani airfoil düşünmüştük, thin airfoil düşünmüştük, küçük u hat, küçük v hat yapıyorlardı. Burada da aynı argümanlar var. Yani normal şoksuz bir süpersonik akışa küçük bir u hat ve küçük bir v hat introduce edecek kadar bir hump var. O kadar sadece. Öyle düşünerek, yani o koşullar altında bir hump var ve bu küçük perturbation generate eden hump hani birden fazla Mach wave oluşturarak o Mach wave'lerin birbiri üstüne binerek bir şok dalgası yaratmasını sağlayacak kadar büyük bir disturbance yaratmıyor. Öyle söyleyeyim.
Anladım sanırım.
Öyle söyleyeyim. Ama güzel bir soru. Yani dediğin gibi theta beta m şeylerinde çok küçük theta deviation şeyleri var. Ama burada olay sırf theta da değil. Olay burada hump'ın mesela yüksekliği burada. Çünkü perturbation velocity'yi create eden şey o mesela. Tabii yüksekliğiyle theta da independent değil diyeceksin. Güzel bir soru. Bu sorunun cevabını da ne düşüneceğim.
İyi tatiller hocam size de o zaman.
Tamam. Peki. Başka sorusu olan? Peki herkese o zaman iyi tatiller, iyi bayramlar şimdiden. Aradan sonra görüşmek üzere.
İyi bayramlar hocam. Dikkat edin kendinize.
İyi günler hocam.
Tamam.
İyi bayramlar.
Teşekkürler. Hoşça kalın.